Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and today we will be continuing with part 2 of Einstein's Revolution, the life and times of Albert Einstein and his scientific accomplishments and legacy. Now, in our last installment, we had just finished explaining how Einstein had revolutionized the world of physics with his general theory of relativity, which combined all of his work up until that point on special relativity and the behavior of light, which reconciled research on electromagnetism with Newtonian physics, and how his expansion of this to incorporate gravity led to a system that has allowed astronomers and astrophysicists and cosmologists to accurately describe our entire universe, to describe how gravity behaves on some of the largest of scales and how the laws of physics change in the presence of extremely powerful gravitational forces, and this became part of our cosmological traditions, and it's lasted to this day. It's been tested 9 ways from Sunday and has always come out on top. And Einstein's work with electromagnetic forces and how the speed of light related to them and how time and space and matter and energy, they're all flip sides of the same coin relative to the observer, this helped open the door to the field of quantum mechanics. And as I was saying last time, a lot of the implications of his work were things that Einstein himself was not too crazy about. He liked to believe in a static, unchanging universe rather than one that was subject to change. He rather believed that the laws of physics allowed for an orderly universe rather than one that was random and chaotic. So, obviously he had some problems with the revolutions he helped inspire. Nevertheless, by the 1920s, his reputation was established and he became internationally renowned. However, his life was about to enter a rather dark phase on account of the rise of Nazi Germany, World War II, and atomic diplomacy. So as I noted in the last episode, 1914 was a big year for Einstein. It's when he returned to Germany and took on the position of the director of the Kaiser Wilhelm Institute for Physics and a professor at Humboldt University in Berlin. And he would remain there until 1932. And by 1919, after 5 years of living apart, he and his first wife, Mileva Marek, the woman with whom he had had 2 sons, would divorce. Shortly thereafter, Einstein remarried to his cousin, Elsa Lowenthal, who he'd remain married to until her death in 1939. But it was in 1933 that Einstein made a major move. He visited the United States for the 3rd time in his life. But whereas the 2 previous visits were all about him conducting lecture series and tours at various American universities, on this particular occasion he knew he was not going back to Germany. The Nazis had taken power in that same year, and martial law was declared shortly thereafter, and the anti-Semitic policies of Hitler and his followers was evident for all to see. And so Einstein became part of a large exodus of scientists, not all of whom were Jewish, as well as intellectuals and common citizens who frankly didn't want to live under a Nazi regime. After 2 months of touring as a visiting professor at various American universities, he and Elsa traveled to Antwerp, Belgium in March of 1933. When they got there, they'd found out that their cottage had been raided by the Nazis and their personal sailboat had been confiscated. And about a month later, Einstein learned that his works were among those specifically targeted for Nazi book burnings, that his science had been termed Jewish science, and he was placed on a list of enemies of the German regime with a bounty of $5,000 placed on his head. Combined with Hitler's massive affronts against German Jewish citizens who'd remained behind, Einstein chose to publicly renounce his German citizenship. And Einstein was in good company. He was part of a rather large community of German and Jewish expatriates, many of whom were scientists in Belgium. For the first few months, him and his wife lived in De Haan, where they lived and worked, and he spent a lot of his time trying to help fellow Jewish scientists in Germany escape persecution. He also traveled to England and contacted several other heads of state around the world, trying to convince them to extend a helping hand to Jewish scientists and provide asylum for them as they fled Germany. And he met with some success. In England, he met with Winston Churchill, who was an MP at the time, or Member of Parliament, and former Prime Minister Lloyd George, who, according to at least one historian, dispatched physicist Frederick Lindemann to Germany to seek out Jewish scientists and arrange for them to teach at British universities. He also wrote personally to Turkish Prime Minister İsmet İnönü and asked him for help resettling Jewish citizens, and as a result of this, roughly 1,000 Jewish German refugees were invited to Turkey and settled there. And by the fall of October 1933, he accepted an invitation to teach at the Princeton Institute for Advanced Study. And he was one of few Jewish professors at the time, given that most American universities had quotas that limited the number of Jewish students and teachers. And in 1935, Einstein applied for permanent residence in the U.S. and received his citizenship roughly 5 years later, and he would remain in the U.S. and at Princeton until his death in 1955. During this period, he continued to find a way to refute the accepted interpretation of quantum physics and develop a unified field theory that would unite quantum mechanics and general relativity. In addition, 4 years later, when World War II began, he played a rather important role in the development of the Manhattan Project. In fact, even though Einstein didn't participate directly in the project, which was overseen by J. Robert Oppenheimer, Einstein was vital in getting the ball rolling. This began in 1939 when Einstein was approached by a group of scientists led by Hungarian physicist Leo Szilard, who warned him that the Nazis had a program to develop nuclear weapons. Einstein then co-wrote a letter to President Roosevelt warning him about this program and urging him to start a similar program so that the Nazis would not be the first to realize the technology. And historians view this as the key stimulus for the U.S. launching its own nuclear weapons program. Einstein also used his connections with the Belgian royal family and Queen Mother to gain access to the Oval Office, whereupon he met President Roosevelt personally to discuss the danger of the Nazi program. As a result of Einstein's efforts, the U.S. initiated the Manhattan Project. Much like Oppenheimer, Einstein would later come to deeply regret his involvement. In 1954, a year before his death, he is said to have shared with a friend, Linus Pauling, "I made one great mistake in my life when I signed the letter to President Roosevelt recommending that atom bombs be made, but there was some justification, the danger that the Germans would make them." But in and around all these really tragic events, there were some very, very bright moments for Einstein. For example, a few months after he published his theory of general relativity, another brilliant scientist produced a breakthrough that predicted black holes. This was German physicist and astronomer Karl Schwarzschild. And when looking at Einstein's field equations, he found a solution that described a gravitational field so profound that even light would not be able to escape it. And this solution came to be known as the Schwarzschild radius. And to break this down, scientists were aware at this point in history that when stars reached the end of their life cycle, they would undergo collapse. And this would arise from the fact that all stars are essentially nuclear furnaces that are constantly fusing hydrogen and helium in their interiors into heavier elements. And when they exhaust that fuel, the energy and outward force that this generates is no longer enough to counteract the massive force of gravity that caused them to collapse and become a fusion furnace in the first place. And as a result, the stars would collapse and continue to collapse until they achieved supernova and blew off their outer layers. Now, whereas smaller stars would leave behind a remnant, a white dwarf, or a neutron star as it's called, a sufficiently massive object, so Schwarzschild reasoned, would collapse into a sphere that was so compressed, so infinitely dense, that the escape velocity from the surface would be equal to the speed of light. Because, as we covered in our last episode, gravity is essentially an acceleration, and the speed of light is roughly 300 million meters per second. So in this case, the object itself becomes so gravitationally strong that its pull is equal to 300 million meters per second per second. Schwarzschild's radius was essentially the radius that a mass would need to collapse to in order to achieve this. And in time, other physicists came to the same conclusion independently. This included English astrophysicist Arthur Eddington in 1924 and Indian-American astrophysicist Subramanian Chandrasekhar in 1931. Based on Einstein's field equations, he also came up with another resolution known as the Chandrasekhar limit. According to this theory, neutron stars that had a mass above this limit would collapse to form a point-like spherical object that would have infinite mass. And Oppenheimer himself also jumped on this train, and he and other physicists indicated that given general relativity, that time and space were relative to the observer, and that gravity, like acceleration, caused objects to experience time dilation as they approached the speed of light, he and his co-authors argued that objects which corresponded to the Chandrasekhar limit and which collapsed to the Schwarzschild radius would form a singularity at their boundary. And this singularity, known as the event horizon of a black hole, anything that fell within it would experience time dilation to the point where time would stop. Meanwhile, to the outside observer, they would be looking at the surface of what was essentially a black star, an object that had become frozen in time at the instant of collapse. And it was only over time that these objects came to be known as black holes, because, when discussing the implications of such stars, a scientist noted that it sounded a lot like the Black Hole of Calcutta, a notorious prison in India from which many people went but none returned. Similarly, black holes were theorized to be objects into which all surrounding matter would infall and never be seen again. By the 1950s and 1960s, astronomers had instruments for the first time that were sophisticated enough to search the cosmos for evidence of black holes. While it was impossible to image these directly with the technology they had, they were able to discern the effects of black holes on surrounding spacetime and objects. This period was known as the Golden Age of General Relativity because of it. These observations also noted far greater examples of what Einstein predicted in his 1911 paper on the influence of gravitation on the propagation of light. For people who heard the first installment, they will remember that this proposition, that light itself, that its path is bent in the presence of a gravitational field, offered a testable proposition, which led to Sir Arthur Eddington's campaign in 1929. Whereas the expedition had shown that light would follow the curvature of our sun's gravitational field, so that a star behind the sun would appear as if it was adjacent to it in the far distance, observations made during the Golden Age of Relativity showed how galaxies would not only alter the pathway that light followed, but also distort and even amplify it. This became a tool for astronomers to look deeper into the universe, known as gravitational lensing. This process involves taking a massive object that's in the foreground and using its gravitational field as a lens to see light from more distant objects. Over time, scientists also discovered how light from more distant objects would be distorted to create strange shapes, known as Einstein rings, in the case of light forming a halo around the intervening object, or Einstein crosses, where light was split and went off in multiple directions, giving the appearance of a cross. As already noted, Einstein's theory of general relativity would become a major part of astronomy and cosmology. In fact, by the 1960s, astronomers began to notice that the rotational curves of galaxies, the speed at which they rotated, as well as the gravitational influence they exerted through lensing, did not match with the observed amounts of matter in said galaxies. Using general relativity as a touchstone, they determined that the gravitational forces at work were far greater than the visible matter would imply. And this led to the theory that in addition to visible matter, space was filled with a mysterious mass that we could not see, that did not interact with electromagnetic forces and was therefore invisible in visible light. This came to be known as dark matter, which scientists calculated would account for 85% of the mass in the universe. Another development in the 1960s was the discovery of the cosmic microwave background, or the CMB. This refers to the diffuse microwave energy which is visible in all directions and at the same distance every time, roughly 13.8 light-years away. The discovery of this background effectively ended the debate on whether or not the universe was created in a single event, known as the Big Bang Theory, or whether or not matter was slowly added over time, known as the steady-state hypothesis. Though Einstein was unable to participate in the debate, proponents of the steady-state hypothesis frequently cited him and his theories, whereas it was George Lemaitre, one of the two scientists, along with Edwin Hubble, who confirmed that the cosmos was expanding, who proposed that if this expansion were traced backwards, it would invariably arrive at a point where all matter in the universe was in a hot, dense state that eventually exploded outwards with incredible expansionary force. This came to be known, jokingly, as the Big Bang Theory. While the term was meant to be pejorative, it nevertheless stuck. Roughly 30 years later, the Hubble Space Telescope was launched, and provided some of the most breathtaking images ever acquired of the cosmos. Among its many objectives, Hubble was to investigate what had come to be known as the Hubble-Lemaitre constant, the rate at which the universe was expanding. Its deep field observations also revealed something very interesting. Prior to Hubble, ground-based telescopes could really only see about 4 billion light-years in any direction. And these observations confirmed that Einstein's theory of general relativity was right on the money. But with Hubble, astronomers were able to see much, much farther. Over time, Hubble was able to push the boundaries of what astronomers could see. In 1995, shortly after it was deployed, Hubble was used to conduct the Hubble Deep Field campaign, where it was able to observe objects as they existed just 1.5 billion years after the Big Bang, over 12 billion light-years distant. These observations noted something highly unusual. Since the 1920s, astronomers had noted that the universe was in a state of expansion. This realization caused Einstein to discard his idea of the cosmological constant, a theoretical force that would hold back gravity, which he called the greatest mistake of my career. But what astronomers saw, thanks to the Hubble Deep Field, was that this expansion had changed over time. Whereas the rate of expansion had remained relatively consistent up until 10 billion years after the Big Bang, for the past 4 billion years it had been increasing. In other words, cosmic expansion was accelerating. This provided vital proof that in fact Einstein had been correct. His cosmological constant did in fact exist. However, the value of it was not enough to simply hold back gravity. Its value was significantly greater than gravity. And as the large-scale structure of the universe continued to expand outwards, the gravitational force that limited the rate of expansion eventually got weaker. In honor of Einstein, scientists commonly referred to this expansionary force as the cosmological constant. However, the term dark energy also caught on, and is more commonly used. This led to new interpretations of Big Bang cosmology. In the past, scientists had argued that, based on Einstein's theories, the universe would continue to expand until all the expansionary force had been exhausted, at which point it would contract. The universe, they argued, began with a Big Bang and it would end in a big crunch. But now, with the discovery of dark energy, they theorized that it would either continue to expand indefinitely, resulting in heat death, where every star in the universe would burn out, or that the fabric of space-time would eventually tear, known as the Big Rip, or that the universe will eventually become a massive void filled with nothing but black holes. Regardless, Einstein's general relativity remains a foundational part of our current cosmological theories, including the predominantly held lambda cold dark matter model. This model takes into account dark matter as a slow-moving, massive phenomenon, aka cold, and includes Einstein's cosmological constant as the lambda. Today, Einstein's theories continue to be tested and even challenged. On the one hand, ongoing observations of the cosmic microwave background and attempts to measure cosmic distance scales using it showed an inconsistency with similar distance measurements made more locally. This has led to what is known as the Hubble tension. This, along with the proposed existence of dark matter and dark energy to explain discrepancies in our observations, have led some to reconsider whether or not general relativity is correct. Alternative theories, like modified Newtonian dynamics, or MOND, have been raised. However, all tests of general relativity currently indicate that it is in fact accurate. This includes the observations of supermassive black holes, gravitational lensing, experiments involving atomic clocks, and many others that have demonstrated for the past century that Einstein was right. Attempts to resolve these discrepancies are among the many objectives of next-generation telescopes, like the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, the Euclid Telescope, and many more to come. In addition, Einstein's failure to find a unified field theory, or theory of everything, has lived long past his death. Essentially, scientists have found that in order to explain all phenomena in nature, they must either turn to quantum physics, which is good for explaining how subatomic particles behave, and general relativity, which accurately explains how large gravitational objects behave. However, to this day, scientists have not been able to find an explanation for gravity on the quantum level. Whereas all other forces in nature have a corresponding subatomic particle or force carrier, attempts to locate a graviton particle, and other theories that look beyond the standard model for explanations, such as supersymmetry, string theory, and loop quantum gravity, have either come up negative or cannot be proven at this juncture. Even the late, great Stephen Hawking could not resolve this problem in his lifetime, so clearly we're just going to have to wait. In these respects, Einstein's legacy lives on. His theories and breakthroughs have provided the basis from which subsequent breakthroughs have been made, and the answers to some of the greatest cosmological mysteries that eluded him continue to elude the best scientific minds of today. In many ways, science is waiting for another such as he to come along and resolve our current set of mysteries, providing the same brilliant synthesis and insight that Einstein did. Like Sir Isaac Newton, Galileo, Copernicus, and Aristotle before him, Einstein's contribution had become foundational and even canonical, and they are likely to remain that way for many generations to come. Thank you for joining me for this segment on the life and times of Einstein, his contribution to science, and his enduring legacy. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.